In this lecture, we will discuss chemical reactions. Chemical reactions occur every time a chemical bond is made, broken, or rearranged, or if we transfer electrons between two or more atoms or molecules. So chemical reactions are written in very specific manners. Okay. So in our example down here, you will notice that we have atoms and molecules on the left and on the right, and we have this nice arrow. Okay. This arrow tells us which way that we are going. So we're going to start over here on the left. These are going to be our reactants. This is going to be what we're starting with. So we have 2 hydrogen molecules and 1 oxygen molecule. And over here on the right, this is going to be our products. This is what we are making. So we have made 2 water molecules from our hydrogen and our oxygen molecules. Now, if this arrow was going the other direction, then now our water would become our reactants, and the oxygen and the hydrogen would become our products instead. Okay, so the arrow again tells you which way you are going. Now you may have noticed that there were several numbers in the formula that we just worked with. Okay, we had some bigger numbers and some smaller numbers. The bigger numbers, we call these coefficients. This tells us the total number of molecules or compounds in our chemical formula. So for example, okay, this tells us that we have 3 of these molecules. Okay, in our previous example, we had 2 hydrogen molecules. If there is no number, it's understood to be 1, so this would be an imaginary 1 oxygen molecule, and again 2 water molecules. And then we have the tiny numbers. These are subscripts. Okay, this tells you how many individual atoms you have in a molecule. Again, if there is no number, it's understood to be 1. So this hydrogen molecule is composed of 2 hydrogen atoms. This oxygen molecule is composed of 2 oxygen atoms. Now this water molecule has 2 hydrogen atoms and an understood 1 oxygen atom. Okay. And then we can determine the total number of atoms for each element through the whole chemical reaction. Okay. So our example up top, we started with the 3 calcium, carbon, and oxygens. So let's figure out how many of each atom that we have. So for calcium, that's the first one we're going to come to. Okay, so there's an understood 1 calcium in each of these molecules, but we have 3 of the molecules, so we're going to need to multiply. So 3 times our imaginary 1 would be 3. So we would have 3 calcium atoms total. Our carbon is the same. We have our understood 1, but we have 3 of these whole molecules, so 3 times 1 is still 3. There's our carbon. Now oxygen is a little bit different. Okay, we have 3 oxygens in each of these molecules, but we have 3 molecules in total, so we have to multiply. 3 times 3 would be 9 oxygen atoms total. And we can do the same thing for our formula we're more familiar with. Okay, so for the reactants, we have 2 hydrogens in each hydrogen molecule, but we have 2 hydrogen molecules, so 2 times 2 would be 4 hydrogens total. And then oxygens, we have 2 oxygens per molecule. We only have 1 molecule, so 2 times 1 is still 2. Let's see how that compares to our products. Okay. Over here we have 2 hydrogens in each molecule. We have 2 molecules. 2 times 2 is 4. And here we have 1 oxygen per molecule, but we have 2 molecules. 2 times 1 is 2. Now, if you were keeping track, hopefully you noticed that the number of hydrogens over on the left in our reactants was 4. And the number of hydrogens on the right in the products was 4. Coincidentally, the number of oxygens in the reactants was 2, and the number of oxygens in the product was also 2. Notice the numbers didn't change. Okay. That's something really important to take note of. Anytime you do a chemical reaction, you do not suddenly magically see something in the products that was not in the reactions. There's suddenly not a nitrogen atom in the products. Where would it have come from? Okay. If you started with a nitrogen in the reactants, where did it go? It has to end up in the products. Okay. So chemical formulas are really about moving atoms around in new configurations. Whatever you start with in the reactants, they have to be there in the products. They're going to look different. Okay. Think about baking a cake. You take your eggs and your flour and your sugar and your butter and you mix them all together. You make a cake. The cake does not look like the individual ingredients, but you didn't lose anything. It just looks different. Now, we have a few specific types of reactions that we want to cover real quick. First is a neutralization reaction. Okay. So we have talked about neutral atoms having the same amount of protons and electrons. Okay. This type of neutralization is a little bit different. Okay. This one covers acids and bases. Okay. So during a neutralization reaction, we take a base and we take an acid and we mix them together. Okay. So our example here is sodium hydroxide and hydrochloric acid. Okay, so if you mix those together, our acid and our base, what you get is a salt and a water. Okay, so acid plus base makes salt and water. Everybody knows water, H2O. Okay. Salt in this case is NaCl, sodium chloride. Okay. This is table salt, so everybody's familiar with this as well. Okay. But here's the thing. You took an acid and you took a base and you made water and salt. Okay. Water is neutral. Okay. It's not acidic or basic. It is neutral. Okay. Now, many of us do this on a regular basis, intentionally, when we take some of these well-known products. Okay. Alka-Seltzer, Rolaids, Maalox, Tums, Mylanta. Okay. These are all antacids. Okay. If you are familiar with any of these, you know that they are used to treat heartburn, or indigestion, whatever you want to call it. What is happening when you're suffering from indigestion? You have too much stomach acid. It's making you uncomfortable. Okay. Could even be coming back up your digestive system. That's where that burning comes from. We would like to not do that. So we take our antacid, so all the stomach acid that we have. Okay. We're going to take our antacids, okay, which are going to be slightly basic. So all that stomach acid that was giving us a problem, we're going to add that base, so we're going to turn it into water, okay, and salts. We're going to neutralize it, okay, so we won't be uncomfortable anymore. Endergonic and exergonic reactions. So we've got our picture up top for endergonic reactions. Endergonic reactions, notice that our reactants are still on the left, our products are still on the right. Okay. What does this big hump represent? Okay. This represents how much energy you have to put into this reaction to make it happen. So endergonic reactions happen when you build molecules. Okay, so notice that we have individual little pieces for reactants. We're going to use ATP to build a larger product. Okay. And not only does this happen inside your body, but this happens outside. This happens when you build a house, when you clean your room. Okay. This does happen when you build new muscles and new cells, things like that. But you can do this outside of your body as well. Now, exergonic reactions are the opposite. Okay. Exergonic reactions, we are going to take a larger reactant, so now a bigger molecule to start with. Okay. And we are going to release energy when we break apart this molecule into smaller pieces. Okay, so now our products are going to be tiny. What we finished with was tiny. What we started with is much bigger. So now we're breaking down. Again, this makes ATP, or energy. This would happen when you knocked down a house, when you messed up your room, if you're breaking down muscles or destroying cells, things like that. Now, if we are specifically doing this only inside of our body, through our digestive system, we're now talking about metabolic reactions. We have two varieties, catabolic and anabolic reactions. Catabolic reactions, which are termed hydrolysis reactions, occur when you break down a large molecule into smaller ones. Okay. So we can take molecule AB and we can break it down into atom A and atom B. So a lot of times you'll hear the terms polymer and monomer. So poly means many, mono means one. So we're going to take our polymer made of many pieces, and we're going to break them down into individual monomers. How are we going to break these? We're going to use water. Okay, so hydrolysis, we said, was another name for catabolic reactions. Hydro meaning water, lysis meaning to break. Okay. So we're going to take water to break down large molecules into small ones. Now, anabolic reactions are the opposite. Okay? Anabolic reactions occur when you take small subunits and you put them together to create larger, more complex molecules. Sometimes these are termed dehydration synthesis reactions. We have our general notation here, our individual monomers. Okay, monomer A, monomer B, we're going to stick those together. We're going to chemically bond them together to form polymer AB. Now we said dehydration synthesis is another name for these. So what happens when you get dehydrated? You've lost water. Okay. So we are going to remove water. It's going to be a product. Okay. Now the synthesis part, what does synthesis mean? It means to make. So we're going to make something by removing water. So we have made a polymer by removing water from these two monomers. Okay. Now put a star by this. Circle this whole page. Highlight it. Make you 12, 15 million note cards just on this one slide. Okay. Students flip these every semester. They get them backwards. Okay. Don't do that. Lysis means to break. Okay. Hydrolysis, you are breaking down a large molecule into smaller ones. Synthesis means to make. You are making a large molecule from smaller ones. Okay. Make yourself a note that this is a commonly missed topic so you don't miss it yourself. Now, all of these reactions that we've been talking about, they go a lot faster and they work a lot smoother if we use enzymes to help with these reactions. Enzymes are biological catalysts that increase reaction rates, and they do this by lowering activation energy. So let's talk about all that. So first of all, most of your enzymes are going to be proteins. Okay, just kind of keep that in the back of your mind. We said they do their job by lowering something called activation energy. Okay, so what does it mean to activate something? It means to start. Okay, and what is the energy that we know and love in our bodies? It's ATP. So enzymes work by lowering or reducing the amount of ATP we need to start a reaction. Okay. Enzymes are highly specific for substrates. Okay. So what does it mean to be specific? It means to be picky. Okay. And what is a substrate? A substrate is going to be what an enzyme binds to. Okay. We're going to do that binding at our active site of our enzyme. So we've got our image. Here's our enzyme, this yellow thing with a very strange shape. And the active site is the strange little part. Okay. Notice here's our substrate. This is what we're going to bind to. Notice that this shape is complementary. Okay. Same thing down here. Okay. Enzyme 1 has a particular shape that will bind with substrate 1. Enzyme 2 is complementary in shape to substrate 2. Enzyme 3 is complementary in shape to substrate 3. Okay? So this is what we mean by enzymes being specific. They're picky. Enzyme 3 is not going to bind to substrate 1. The shapes have to be complementary. Now, enzymes do not alter the reactants or the products. The reactants and the products work all by themselves. In fact, the reactants and the products, that chemical reaction would happen regardless of whether the enzyme was there or not. Okay. Enzymes just help bring reactants together to form products. Last but not least, enzymes are not permanently altered in reactions themselves. Okay. So if enzyme 1's job is to bring these two substrates together so we can join them into one bigger molecule, great. Once that happens, once these are joined and become, product 1, this enzyme will release that product, and this enzyme will still have this particular shape, and will be able to move on and find new substrates to assist with a new chemical reaction. So we can recycle these, we can reuse enzymes. Now, eventually, they do have a shelf life, just like everything. Okay, enzymes are not immortal, but they can be used multiple times before they need to be broken down, and we create new ones. Now, why do we care about enzymes? Well, because if you don't have an enzyme or your enzymes don't function correctly, you could suffer from particular disorders. Okay? The most common one that people are familiar with is lactose intolerance. Okay? So lactose intolerance, you do not have the ability to break down lactose, which is milk sugar. The normal enzyme that would break that down is called lactase. Okay, so many enzymes end with ACE, A-S-E. If you do not have lactase, you cannot break down lactose. Anything that you put into your body that you cannot use or break down causes your body problems. So if you or someone you know suffers from lactose intolerance and they consume dairy products that have lactose in them, most people know that eventually that is going to cause a lot of discomfort to their digestional tract, lots of uncomfortable symptoms. Okay. That one's uncomfortable, but maybe not life-threatening. Some of these other ones, Tay-Sachs disease, SCID, severe combined immunodeficiency, PKU, phenylketonuria, these can be or are for sure fatal. And in each one of these, you are missing one or more critical enzymes to some sort of metabolic process in your body. Okay, we mentioned the activation energy. We wanted to look at an example real quick. So our reactants in this equation, we've got carbon dioxide, and we're going to add water to make carbonic acid. Okay. So you will notice that the red line, without an enzyme, this reaction will still happen. Okay. You just have to put in a lot of energy to make it happen. That's a lot of ATPs that we could be using somewhere else. So if we instead use an enzyme with our blue line, notice that our reaction still happens. Still get the same product. Okay. We have less input of energy. We didn't have to use quite as many ATPs. which means we get to do this a lot faster because we didn't have to wait and wait and wait to gather up all these ATPs to make this happen. Okay, instead of using, I don't know, 100 ATP and waiting to find those 100 ATP, maybe we found 10 real quick, we got our enzyme going, boom, we're already done. Okay, so again, these reactions would occur with or without the enzyme. We just get to go faster and we get to use less energy if we do use our enzymes.